Hello, everyone. My name is Gil. I am the Senior Applications Engineer at DfR Solutions. Today, we're going to talk, as Adita said previously, we're going to talk about some system-level effects and how to model them in printed circuit cards. So we'll talk about overconstrained boards, which is a type of issue with system, which is a system-level effect. We'll talk about coatings and underfills. Conformal coating used as underfills in general, and we'll talk about mirrored components a little bit. So let's talk a little bit about what is a system level effect versus a board level effect, and actually what is a component level effect. So when I think of a system level effect, it's not something that is internal to a component. So for example, a BGA has a die size, it has an overmold material, it has laminate material like for the substrate, ball sizes, ball pitches, all of those things are component level effects. So those things are the decisions were made by the component manufacturer, and you really don't have that much effect for it. The board level effects are anything that you can do. So for example, the board laminate material selection, component placement, where are the mount points, how it interacts with the environment. The system level effects are things that happen on a more global level. So these are things that are not the component and not specifically the component connection to the board. These things, you might not have the ability to even design that. As a board designer, you might not even have input into what goes into that. So one of the big ones is the case effect. The design of the case and the design of the board need to be integrated into one another, especially as we're moving to more high-density boards. The way that we do underfills and coatings also has can have a large effect, and sometimes the people who choose the components are not the same people who choose the underfill and coating. This happens a lot in the, it's happening more often in the automotive industry, but this happens a lot anytime you're doing a COTS board. So if you're grabbing a commercial off-the-shelf board and you're putting it into your system, some kind of network router or some kind of controller or something like that, and you're putting it in your system, you might have a higher vibration environment, and a lot of people decide to underfill the components in order to make them more robust for shock and vibe. The problem is there's a trade-off there. So we'll talk more about that, and then we'll also talk about component mirroring. So component mirroring, you do have an effect on it. Well, sometimes, most times, not always, but essentially what happens with component mirroring is that just like you see in the picture here, you have a component on one side of the board and you have a component on the other side of the board. And we'll talk about that effect in the end. So why are system level effects even a problem that we talk about? So there are more and more companies that are seeing failures for no reason, like completely outside of what happens in the test. They're seeing it either in the field or sometimes even due to manufacturing processes. And the idea is this. So for thermomechanical problems, ideally, what happens is what you see on the left. You have a CTE of the component, which for a QFN BGA can be anywhere between 8 to even like 13 or 14 ppm. And you have a board that is anywhere between 13 to 17 ppm. And ideally, what happens is that the board expands as a rigid body, meaning it doesn't bend. And then the component expands as a rigid body, and you have a pure shear strain, which is a delta alpha delta T effect. Now, if you start adding all kinds of system effects, the board itself might actually be bending. Or not only that, even just because of the way the construction is and because the board is deformable, the board itself might be bending, the component itself might be bending, and then you have the output into the solder balls or into the solder joints is that you have some kind of shear combination, but then you also have the tension and compression. And solder behaves differently in tension than it does in compression. We call this triaxiality or triaxial load or mixed mode loads. All of these things, if you Google them, you will find some kind of answer that kind of looks like this. The problem with that is that everything we've ever done, all of the modeling we usually do, is correlated to pure shear loading, CTE mismatch between the board and the component. So when you do your test and you do it to a board, everything looks okay. And then when you put the board on top, inside of your system, everything breaks. And this happens a lot because it's easier to run a test on a board because the thermal mass, the amount of material that needs to go up and down in temperature, is only the board and the components. When you have to do this for a whole entire system, the thermal mass is much, much larger because you have, the case around it. That takes a longer time. So usually you try to kind of prevent running that test as much as you possibly can, or you delay it as much as you possibly can. Sometimes you don't even know what the case is going to look like, and manufacturing the case takes time also. So the problem is, by the time you get to manufacturing the case and manufacturing the board, putting them together and putting the whole thing in a chamber, or even if you're just doing liquid to liquid thermal shock, by that time you have spent a lot of time and money on those boards. And if you have a failure, that is a big deal. So that's what we're trying to solve. And I got kind of like a graphic thing for interaction of the board and this is kind of the same, the interaction of the board and the aluminum plate. So this slide shows the interaction of the component and the board. This shows the interaction of the board and the aluminum plate. And that's also one of the places that you can get where you get bending in the board due to the CT mismatch between the board and the case. Now, I used aluminum in this case because it's very common, but the reality is that we have all kinds of polymers, all kinds of acrylics, all kinds of PVCs that will create a similar effect. Aluminum is egregious because it has a relatively high CTE, and it's really, really strong. So aluminum compared to the board, it's really stiff. If the aluminum is doing something, it's just taking the board for a ride. There's nothing you can do to mitigate that as a board designer. And I'll repeat that several times. You'll hear me say that several times. One of the other things that happens is we kind of forget, when we connect the board to the heatsink or to the case or to the housing, then we're doing this usually at room temperature. If we do a hard contact between them, if we make them hard, then it means that when it shrinks, you actually have the board being subjected to, from the cases, being subjected to a compressive load, and it'll buckle like a beam. And that one is sometimes can be worse than the effect what happens when you stretch the board. So let me go back a little bit into history of how we got to this place. It's kind of funny. We used to have heat sinks like you see on the top right. That's what they used to be. It used to be a small thing connected onto a single component, and it basically only affected that component. It was glued to the top of it, and that's that. Nowadays, the heat sinks is what you see on the top left, which is a little bit more interesting. And in general, we see cases that are directly connected to boards. So when you do something like this, and the entire weight of the heatsink is sitting and it's supported directly by the case, so everything has a hard contact between a huge heatsink and the case and the board, then you start having problems. And these early failures that you see, these are cross-sections after like 400 cycles, 200 cycles. I talked to people over the last couple of years. I've been talking to people, and they basically said, well, we used to make a heat sink for one component. Now we have more components that are dissipating heat. So we just made the heat sink bigger, but we still kept it as only, glued down to those components. Or we only kept it with the 4 staking points for the aluminum heatsink. And they never thought about what happens to the aluminum versus the board because it's never been a problem. So somewhere along the way, we kind of forgot how to design for case interaction with the board to prevent these early failures. So let's take a look at a case study of a overconstrained board. This is what's inside of an SSD, and I kind of made a Sherlock model of it, and in this case, I decided that the board CTE will be 17.4. And I applied a minus 40 to 125 temperature difference. So I basically said Let's see what happens when you heat this whole thing up, and you can see the 4 mount points that it has along the edges of the board. If you take a look at the results after, obviously I removed the case so we can see only the board strain. So you can't see the components, you can't see the case in here. And you can see that with the aluminum case, the total strain on the whole board is much, much higher. The individual components, the big BGAs in the middle, so it's this guy right here and this guy right here. So these two BGAs, they still have the same localized CTE mismatch that I talked about before, which is component versus board. And you can see that right here. And their strains are kind of the same. But all the other components, because the aluminum case is stretching, all the other components are exacerbated. So where before we didn't really put any strains on the other components, now that we put it in the case, we're breaking everything. Or we have a higher probability of breaking the TSOP components, which are the NAND memory. So that's kind of a very quick way of doing an analysis, which is automated with the thermal mechanical module inside of Sherlock. Now, if you're doing this in Abacus or ANSYS or any other one, what you're trying to do is you're trying to do a static structural analysis where you apply a base temperature and you go up to the highest temperature. So in this case, it would be the temperature of your, the highest temperature in your test. You can also do an environmental test, which would be environmental modeling, which would be the highest temperature in your environment. If your environment is kind of like think of a data center or some kind of big server farm, then you don't necessarily get up to the temperatures that you see in the test. So the early failures that you see in the test might not actually be correlated to what you see in the field, because in the field you'll only go up to, let's say, 60 degrees. And that delta T might not cause enough problems for you. So there's two things that you can see here. Number one, you can shoot yourself in the foot by running an analysis on temperature that don't exist in the field, and therefore you're going to have failures in test, but you're exacerbating the wrong failure mode because it would be an overstressed failure mode due to CTE mismatch between the case and the board. In the field, you might not have those high delta T's. It might actually stay at the same temperature pretty much all the time. So it's different if I'm putting this SSD in a desktop versus a server farm versus, I don't know, a self-driving car or something like that. So if you're doing this, if you are actually trying to do this in Sherlock, Sherlock has integration to Abacus, SolidWorks. You can bring in the case. So let me show you this. I brought in this green case, the aluminum case. I brought this in directly from Abacus, or I can bring it in from SolidWorks as well. And then I can solve the whole thing inside of Sherlock. You can also solve it outside, do it independently, completely. You can also do this in ANSYS as well, or Nastran, or any other solver that you find. So one of the things that we can do to mitigate this kind of problem is to use something called shoulder bolts. So if I took the 4 mount points that I had, and I kept one of them as a hard contact, let's say it's a ground contact as well for electrical purposes, the rest of them I can keep as shoulder bolts. Now, if you design the shoulder size correctly, then you can make it so it's a little bit difficult with the tolerances, but you can force it so that your board doesn't actually move that much in the Z direction, meaning during vibration and shock, you have a good mitigation for vibration and shock, but there's enough of a gap between the shoulder and the inside of the hole that if the board is trying to expand, it's not hard for it against it doesn't meet the bolt itself, so the bolt doesn't bite into it. And I've seen it where I took the bolts out, and you can see inside the copper, the plated through hole for the mount point, you can actually see the striations of where the bolt was biting into the copper. You don't want to do that. So a shoulder bolt with a slightly smaller shoulder than a shoulder diameter than the hole diameter, the inside hole diameter, and you want a small gap. You want to design it so it has a small gap between the bolt, the bottom of the bolt head, and the top of the board. Some people put nylon washers in there to even help the friction more. I don't think that's necessarily the best way to go because it's expensive and it's going to be hard to get it to a project manager to actually agree to it. So that's one way. The other thing that we can do is we can use slotted holes. So slotted holes, or just oversized holes, basically, are anything that allows the bolt, the board to move a little bit in the direction that it needs to expand. This usually works for really large boards. You kind of have to do these oblong holes instead of just trying to create a large drill hole. What you do is you make a slot, and then for large boards that usually expand in one direction, out from the center or out from wherever it is that you're mounting it to the universe, to the case, wherever you have the hard contact, you are basically creating a slot that allows the board to expand more in one direction than the other. It's possible to, there's a trade-off to everything. It's possible to actually decrease board reliability if you improperly mount the board. So you're trying to mitigate vibration and shock while at the same time not messing yourself up for thermal cycling. The cool thing is that we can actually predict the effect of improper mounting. So you can do this experimentally. You can put a strain gauge on the board and then run it in temperature and see if it buckles or stretches. It shouldn't, you should be able to do a board with the case, board without the case. They should be the same. If you're doing it right, then the strain on the board should be exactly the same because it's only the thermal strain. We can also predict some of the failures due to bending. Unfortunately, it's not that easy. It's not that straightforward. We have some equations that we can use. We have some strain equations. We're not 100% sure on how it works when you're doing these triaxial effects on solder. Again, remember I was talking about if it's loaded in shear, it's one thing, but if you're doing tension and compression, solder behaves differently in compression than it does in tension, so it's not a fully reversed load anymore. Solder behaves the same in shear because, you know, shear goes left to right or right to left. But when you're doing tension and compression onto a solder joint, it's a little bit of a problem. All right, so this is kind of overconstrained boards, and we know that we can prevent this whole headache if we just use proper mounting conditions. Let's talk about underfills and conformal coating. So we use edge bonding, corner staking, underfills in order to mitigate the problems due to shock and vibe. Again, just like the overconstrained board, if you're loading the solder joint in tension, compression, and shear, then you're basically asking for trouble. And this can be BGAs, QFNs, TSOPs, QFPs, whatever it is that you're doing. You're basically letting a hard material get underneath your BGA or your QFN. And as that hard material with a high CTE expands, it's basically expanding against the solder joint. And if it expands more than what the solder joint wants to expand, then it's taking the solder joint along for the ride. So I'll say this many times. Good underfill is good, bad underfill is bad, and conformal coat is not underfill. Let me show you some stuff. We did an experiment. We took some components. We did a test vehicle with 60 BGAs. We took 30 of them and we did the regular conformal coat, just standard conformal coat. On the right side, what you're seeing, which is kind of a bad picture, but it's because it's UV light, when we expose it to UV light, the right side, we put really thick conformal coating on it. So these are all the BGAs, and they have super thick conformal coat. And on the left side, it's just regular conformal coat according to the industry standards. The thought was, we've seen this enough times where people say, well, if a little bit of conformal coating is good, then a lot of conformal coating is better. Or they say something like, well, we already need to underfill or edge bond or corner stake. We already need to underfill the BGAs. Why not just use the conformal coat to underfill the BGAs as well? That's a problem. And let me show you what happens. When you do a regular solder fatigue test on a ball that has no conformal coating at all, so that's my control, the one that says no coat on it, what you get is a regular solder fatigue BGA crack, and you can see it cracking along the bottom from left to right there. You can see the cracks along the bottom. Excellent. That's exactly what it's supposed to look. When you do standard conformal coating, so you just use the standard process, you can see that you get kind of the same. It didn't really have a big effect on the performance of the BGA. When you use thick conformal coat, look at what happens to the ball. The hard acrylic that has a high CTE at low temperatures was smushing the ball, and that's a technical term, was smushing the ball to such a degree that it plastically deformed the entire ball. And as soon as it went to high temperature, it was, again, high CTE, hard material. It was pulling away at the whole ball. So basically, that's really a bad thing to happen. And this is experimentally determined. Obviously, we can do this with Sherlock, or we can do it with any other kind of SEA tool that you would like to use. So if you're doing staking, you can show that not all is doom and gloom. If you use the right kind of underfill, you can get actually a better performance due to staking versus non-staking of the same component. So, and Sherlock can show that with the edge bonding, you can actually improve the lead strain, which is basically improve life. Because again, remember, the tension and compression, we don't exactly have a correlation to how long it's going to go. You have to determine that experimentally, but if you want to know directionally, you can show that it's good. So as I said, good underfill is good, bad underfill is bad, and conformal coat is not underfill. Let's talk a little bit about mirrored components. So essentially what happens in with underfill, there's not much you can do if you're not the person who determines if the underfill goes in. If you have any kind of input as to what goes onto the underfill or to the manufacturing process, then you should choose the right kind of underfill and just do the simulations or do the test in order to determine that your underfill is okay. For mirrored components, it's a little bit different because this, you absolutely, as a board designer, have the ability to change it. The reason I call it a system level effect is because we kind of think as the component interacting with the board. And that's kind of when we think of board level reliability. All the tests that I do, if you go to TI or Amcor or Qualcomm or any one of their test results, it's always a component sitting on a board. Even when we did the BGA with the conformal coat and without the conformal coat, these were not mirrored BGAs. There was no mirroring effect. So we kind of think of the board interacting with the component, and that's it. The reality is that when you mirror a component, when you put another component on the other side of it, the component is interacting with the board, the other component is interacting with the board, but it's also artificially stiffening the board in that location. Which means that now the component thinks it's seeing a board with a certain CTE and modulus, but the reality is it's seeing the board with the same CTE but with a much higher modulus because it has a component stiffening up the other side. So we can test for this. We can actually model this. Here at DfR, we modeled components with mirroring and without mirroring. And we saw that overconstraining the PCB, which basically means when we create a mirroring effect, it's exactly the same. So it has a larger strain for the solder joints along the distance to neutral point, which means along the diagonal. It's a fancy way of saying along the diagonal. And this is a 17 by 17 BGA. So you can see that the magnitude of deflection is different, which means that the strain is different for the same board. If you look at specifically at the strain and the strain energy density, you'll see that it's much higher when you have the mirrored. So if you're looking on the left side, you'll see that the strain goes to 0.117 versus 0.147. And if you're looking at the strain energy density, again, in that same corner, you'll see that the effect is 3.2 versus 4.3. So it's a much higher strain, it's a much higher strain energy density accumulated in every cycle, which means that you're accumulating damage faster. This is exactly the same as what happens when we take a board and stiffen the board. So if you do this same thing and you just stiffen the board and without a mirrored component, you get the same result. So on the right side, we have the mirrored component. On the left side, we have the single-sided component, and you can see that a mirrored component will have a higher strain. What happens if I don't exactly mirror them the same? So I can actually take a board that has a large BGA on one side, and I'm putting a smaller BGA on the other side. The large BGA won't feel the effect because it has a small BGA on the other side. But the small BGA is almost connected to the super stiff board. So that's the one that's going to have the early failures. So, and you're going to think, oh, well, that BGA is wrong. No. Your system is wrong. You put that BGA in a location where you caused it to have too much high strain. Not only that, when you mirror components, you're basically creating a location where there's going to be a high strain due to the discontinuity. And let me show you. Right here, in this location, everything here is stiff underneath the components. But out here, it becomes a geometric discontinuity because you have something connected here, and then you have nothing connected to the top here. So if you put components very close to this mirrored BGA, you might have secondary effects on other components that have to do with the mirroring. So just remember that mirroring can have multiple effects as well. Usually what we look at is we look at mirrored BGAs because that's how memory happens. So people who design memory, they like to design memory so that the network latency is exactly the same. So they have the component on the top and the bottom at exactly the same location. Okay. If you're looking at trying to look at the effect of mirroring inside of Sherlock, it's a straightforward, the same way that you would do it in any other software. We can capture that effect with Underfill, without Underfill, and board level effects as well. If you are looking at what Sherlock does for you in general, remember that so those of you who don't know what I'm talking about when I'm saying Sherlock is a physics failure-based design for reliability. We call it reliability physics analysis software. And the idea is I want to predict failure early in the design process as quickly and as accurately as I possibly can. And we are only focused on electronics. We don't do airplane wings. We don't do tires. We don't do nuclear reactors. And then we can look at thermal, mechanical, and manufacturing risks as well. So this is my, if you remember nothing else, slide. So if you were kind of falling asleep and just now paying attention, there are system level effects that we can look at. Overconstrained boards, there's nothing you can do as a board designer to prevent something from bending your board. If your board is being bent by an outside force, it's not because you designed the board wrong, it's because the outside force, it needs to be designed to protect the board from those kind of loads. You shouldn't bend the board, you shouldn't increase the temperature of the board. That's just how board design, you can't really do much about it. If you know your board is being bent by the outside world and there's nothing you can do to prevent that, try to design the board in such a way that it bends in a location where it causes the least amount of damage. The way we do that, we can mitigate this effect by using shoulder bolts and oversized holes. We can also use underfills and coatings in order to mitigate vibration and shock effects. The problem is that sometimes we use the wrong underfill. So remember that good underfill is good and conformal coating is not underfill. If you do have conformal coating, if you have thick conformal coating, try to not let it get under your components. If you're in automotive, aviation, any kind of high reliability environment, especially high regulated industries, you might want to mask out your BGAs and QFNs and just basically not let any conformal coat anywhere around them at all. Just don't conformally coat them at all. Or just underfill them and then conformally coat them. And we know the effect of mirroring components. It changes the whole mechanical system for the component to board interaction. If you know the effects of mirroring, you can design your board accordingly. If you have the ability to crack the width, you will be able to tell your board designers to change the location of their BGAs. It's very difficult to do it because usually the electrical designers will prefer network effects, the electrical effects for speed rather than doing it for reliability. It's a lot harder to design for them to design a board if they can't put the two BGAs exactly one on top of each other. At this point, Edita is going to ask me the questions, and I will answer them.
Sounds good. Thanks, Gil. Mirrored BGAs have been shown to improve or reduce BGA life depending on the pitch offset. In other words, if the mirroring is changed by as little as half a pitch, the fatigue life of the mirror BGA is changed. I've seen such data before. What do you attribute this effect to?
Excellent. So that's exactly how, in order to design a good mirrored BGA, here, let me show you what I mean. So let's take these two, right? So let's say that I put them exactly one on top of one another. So remember that geometric discontinuity that I was talking about right here? So imagine that this is a hard geometric discontinuity, right? Because you have two BGAs and then you have nothing over here. But if you take this BGA and now you start moving it, and you move it, by a little bit first, 1 millimeter, 2 millimeter, 3 millimeter, 4 millimeter. At some point, you will find that they have a larger or a smaller effect on one another. Now, if they're exactly the same component, it's kind of different than if you have dissimilar components. What I'm seeing in automotive is that I have a big BGA on one side and then all kinds of small BGAs on the other side. For memory, what I'm seeing is this configuration. So when you have this configuration, we can all agree that if the BGA on the bottom is far enough away from the BGA on the top, there's no problem. That's not going to be an issue. Everything's fine. They don't even interact with one another. The question is, how close is too close? So we've seen that the worst case is when you mirror them perfectly because of the geometric discontinuity, because of the material discontinuity in your whole assembly. The whole mechanical system has changed. If you change it a little bit, you will see that the effect goes down, meaning the probability of failure will go down. And then at some point, it might actually go up as you get closer to corner of the BGA. So if I take this BGA and I move it where this ball will be just underneath this ball, so all the way over to the right, we actually see it going down and coming back up. Now, we've done some of the simulation work on this to show kind of the effect of half pitch or, slightly staggering them. And you'll see that there are several designs out there of SSDs. You can probably find those pictures of that's exactly what they did, and they did it for that purpose. For a very small amount of design in the electrical side, on the electrical configuration, you get a huge increase on the reliability side. So that's exactly what I attribute it to.
Sounds good. Can you model shoulder? I'm sorry. Can you model shoulder? I'm sorry. Can you model shoulder bolts as a constraint in Sherlock? Absolutely.
So we have this automatically in Sherlock. If you look into the mount points, when you do edit mount points, you will see that there is a chassis material. If you make that chassis material aluminum and then you disconnect the X and Y constraints, I think I had a picture of it. Let me see. Did I have a picture of the mounting conditions? I had it somewhere here. If you disconnect it from the mount point, then yes, you can exactly do that. There it is. So you see right here, if you undo the X and Y constraints in the FEA constraints for any one specific mount point, you can actually virtually do the effect of the case. Not only that, in Sherlock 6.02, you can actually determine the case material, so you can do an X, Y, and Z, when you do the X, Y, and Z constraint, Sherlock will say, well, I don't actually model an aluminum plate, but I'm going to force the mount point to move as if they have a aluminum plate attached to them. So yes, the answer is absolutely yes.
Great. And next question. What parameters determine good underfill?
Excellent question. So the correct answer to any engineering question is it depends. So let me tell you what it depends on. If you're doing a BGA or a QFN, you're really trying to match the CTE of the underfill to the CTE of the solder, which is not, impossible. It's doable. Another thing you're trying to do is you're trying to make sure that the TG, the glass transition temperature of your underfill, is nowhere close to your operating conditions. So if you're going from, 25 to 65 and your TG is somewhere in the 90s or 100, you're fine. But if you're going all the way up to 85 and you have a TG in the 90s, that's a problem, because the TG effects of underfill are well known, where it'll basically rip components right off. It'll rip solder joints. There's another thing that goes into a good underfill when you're doing the QFP, for example, anything that has leads. The problem with that is that now you're trying to match the solder and the leads. So it needs to be closer to that of the leads, and depending on the lead material that you have. QFPs are slightly less susceptible because they have a little bit more flexibility. What we also try to do is we try to get the underfill itself. Sometimes we'll only do edge staking because for it's a little bit, or corner bonding, it's a little bit more, process control, and it's a little bit harder to do if you're having your board manufactured at a board shop that isn't exactly, or an assembler that isn't exactly good at that. But doing edge staking has been shown to be almost as good as underfill, and it doesn't create as much stress on the entire assembly. So there's ways of doing good underfill. I hope that answered your question.
Sounds great. Next question. You present acrylic-based conformal coat data. Do you have any data on silicone-based conformal coating getting under BGA?
So I don't specifically have that data, but we do have that data in general from other people who have published it. I don't think we at DfR look too much at silicone. One of the problems with silicone is that it's super soft. So depending on how much it wicks underneath the component, if it's really, really soft and it's only at the edge of the component, so meaning the viscosity of the silicone wasn't low enough that it went underneath, or it was too low that it didn't go underneath the BGA all the way, it means that you're only getting edge effects of the silicone. And because it's super soft, it can expand outwards. The problem is when silicone gets all the way underneath the component, and then it has nowhere to go. So it can't all of it go out through the sides. So it some of it has to go up, or some of it has to like balloon the inside of underneath the BGA. And as I said the word balloon, all of you became pale and said like, oh no, that is an awful thing. Yes, that is exactly right. You don't want that silicone underneath the BGA. Now, if it's super, super soft, it's not going to matter. If it's like the stuff that we see sometimes in power modules that is really soft and you can basically deform it just with your finger when you touch it, it might not even be a problem. But you can do an analysis on it. You can see if it moves or not. But sometimes those super soft silicones, they're just not enough to do the mitigation for vibration and shock. So you kind of have to make sure there's a trade-off here.
Got it. Another question. Not sure if that was answered already. How do you keep the conformal coat from going under the components?
So there's a couple ways of doing it. Number one, you can mask it. You can mask the component. Basically, the way conformal coat is applied, think of it as like spray painting, right? So you basically put a tape over the BGA that you don't want it to get into. You spray paint the whole thing, and then you didn't paint the BGA. Another way to do it is to just basically put some kind of soft silicone, really, really soft silicone along the edges of the BGA, and then conformal coat the whole thing. The soft silicone allows the conformal coat to go on top of the BGA, and then it doesn't let it go underneath the sides though. So you see, you're kind of like edge bonding the side of it. And the only reason you're putting it there, it doesn't help with mitigation or anything like that. You can also do a hard underfill or like a good underfill, and that way your underfill doesn't really, interrupt. The problems that I've seen, if you put a correctly applied conformal coat, shouldn't be a problem at all. As I've shown you in the experimental results that we ran here, the problems usually arise when you apply a thick layer of conformal coat. Imagine that spray can. If you have a panel of boards and you're spraying it left to right, the middle boards get more conformal coat than the sides. Sometimes they just apply it with like a paintbrush, which is a whole other issue, right? It's a manufacturing issue. So depending on how it's applied, if you have like 2 millimeters of conformal coat and it went underneath the BGA, that's a problem. So you can prevent it by masking or by pre-underfilling it.
Sorry, Gil. Did we answer why avoid conformal coating BGA devices?
I'm not saying to avoid conformal coating BGA devices. What I'm saying is that conformal coating is not underfill. Do not try to use conformal coat as underfill. If you conformal coat and you do a thin conformal coat like you're supposed to, you saw there's no difference between them. Here's the results that we saw. This is our experimental result. No issue whatsoever. This is a standard conformal coat. Looks exactly the same as our control. You're getting the same exact performance. No problem. If you have a thick conformal coat that gets underneath the BGA, that's a problem. So in order to prevent that, some people, they know they can't prevent it due to, the conformal coat being very thin material, so it wicks underneath. It has like a capillary underfill effect as soon as it goes in there. So basically, if you even have the side of the BGA exposed, it'll go there. So people are saying, well, we'll just mask out the BGA so we know that there's no conformal coat underneath it. So, but if you do it correctly, if you apply it correctly, there shouldn't be any problems.
You say conformal coating is not underfill. What about thin film conformal coating, like paralleling?
Absolutely. Yes. Yes, absolutely. It is conformal coat, but it's not underfill. You can't use that conformal coat. Will not help you for vibration and shock mitigation. The reason we put underfill underneath components a lot of times is because we want to mitigate the effects of shock and vibe. So we're kind of holding the components in place so they don't break. But we usually have a trade-off between shock and vibe and temperature cycling. If you're doing a conformal coat, you're basically preventing humidity effects. You're not doing anything for temperature cycling, as you can see in the current slide, and you didn't underfill it, so you're not actually mitigating. So it's the thought process of trying to use conformal coat as an underfill or accidentally getting conformal coat as an underfill. That's the real problem. If you use conformal coat correctly, no problem.
Excellent. Thank you, Gil. We are out of questions. So if you have any additional questions, feel free to email Gil directly. And with that, we'll be ending today's webinar.